Hello everyone. Today I will give you a presentation on our explainable AI research, which is interpretation of lesional detection via a counterfactual generation. And then we will give you a walkthrough on our code implementation. My name is Sung Kim from Image and Video Systems Lab at Korean Advanced Institute of Science and Technology. Our advisor is Yong Man. Deep neural networks have shown great advances in various computer vision tasks. With the tremendous progress, a lot of deep learning-based applications require frameworks of understanding the black box properties of DNNs to exploit them on real-world systems such as deep learning-based medical diagnosis prediction. One of the efficient ways to explain DNS decision is visual explanation. However, in medical datasets, inherent class imbalance exists, thus it makes it difficult to provide detailed visual explanation. To handle such ill-posed medical data distribution, we introduce a novel interpretable framework, Counterfactual Generative Network. Here is the overall architecture of our framework. When an input image is given, the inference is proceeded to make decision of the existing pneumonia detection network. Here, we devise a training procedure, counterfactual manipulation, which deliberately flip the network prediction and feed the modified prediction into the generative network as a prior information to generate fake lesional images. By subtracting the original network from the fake images, we can obtain an attribution map of suspected lesional regions. To generate manipulated prediction of existing network have decided, we literally flip the selected target class prediction. For the normal inputs, the selected target prediction is modified to 1 to occur the certain lesions. Note that the selected target number is randomly sampled. For the generative network, we adopt UNet-based architecture. The manipulated prediction from counterfactual manipulation procedure is fed into the decoder as a prior information, and it is concatenated with the latent feature. Using the adversarial training, we can obtain the generative network to generate more realistic fake lesional images from normal input sources, and vice versa. The adversarial objective function, we add other loss functions to generate more detailed fake images from the original source images. First, classification loss is applied to predict manipulated labels for the fake images, and L1 reconstruction loss is utilized to guarantee the fake images to be analogous to the input images except the lesional regions. Next, as a regularization term, total variation loss is adopted to reduce visual artifacts in the generated images. In summary, the full objective function can be described as follows. In this paper, we utilized two chest X-ray datasets, chest X-ray 14 and vein chest datasets, to compare the precision of the visual explanation with existing methods. As in this figure, our proposed method can elaborately provide more detailed visual interpretation for the suspected lesional regions. In this figure, we selected a certain lesion class infiltration for the counterfactual normal and lesional image generations. We can observe that CGN can change particular region of the lesional input images around bounding box annotations. For the opposite case, we manipulate the prior conditions of the given normal input to infiltration class and generate corresponding lesional image. The annotations for the normal inputs do not exist, but we can infer that the suspected regions by comparing the generated attribution maps. For quantitative comparison, we use two measurements of localization and pixel importance of generated attribution maps, which is energy-based pointing gain and deletion gain metric. As in these tables, our proposed method shows the best performance among the existing interpretable frameworks. In conclusion, we propose a novel interpretable framework, Counterfactual Generative Network, to provide detailed visual explanation for the medical dataset. And we devise a novel training procedure to handle skewed data poses in medical datasets, counterfactual manipulation, which can manipulate majority normal source image to various lesional classes by injecting manipulated prediction as prior condition. And extensive experiments demonstrated that our proposed framework can provide detailed visual explanation both in qualitative and quantitative measurements. We will give you a walkthrough on the code implementation. we have created a GitHub page. So if you want to access the source code, the link is provided. And if you want to download the chest X-ray image dataset, the link is also provided here. The code is implemented in Python, and the dependencies of it is as follows. The input and output for the implemented model is pretty simple. First, if you provide an original chest X-ray image, which includes lesions to the model will give you two different outputs. First one is the generated image, which we expect to be normal, and the difference map, which has information on the lesional region that we want to find out. The algorithm flow is as follows. We uploaded 7 files on the GitHub page. If you run the main file, it will call the GAN class. The GAN class will try to build model and try to load checkpoint weights. Once the checkpoint weights are loaded, the GAN class will try to retrieve data set from the data loader. And finally, it will output the generated images. The main file will call the GAN class and build models and proceed generation. We have set it default directory for the dataset, but you can modify it. Here we define the GAN class. GAN class includes several methods to build models and load checkpoints. This is the generation method of GAN class, which is called in the main file. The flow is as follows. So first it will try to load parameters from checkpoints, and it will print load fail if the checkpoints are not loaded. And it will try to initialize the data loader, and then finally it will iteratively generate chest X-ray images. So we used testnet 121 for the backbone network, and we simply modified the classifier to classify 14 different classes of our chest X-ray dataset. And here we define convolution layers and deconv layers for UNet implementation. The implementation is the same with the UNet, but the difference is that in the middle we concatenate the conditioned vector to the encoded latent vector Z. And here's the implementation for the discriminator. So this is the flow for image generation. First, we disable gradient tracing, and we select one image from the batch. We forward the backbone network to acquire the prediction output, and we create the conditioned latent vector to insert into the UNet structure. And finally, we check if the backbone network detected the lesion correctly. Once we find out that the backbone network classified the lesion class correctly, we generate the normal image from the GAN model. Once we have the generated image, we save the difference map and draw a bounding box to output the image. And this is the GitHub page we have created, and you can find more details on this page. And this is we have prepared for today. Thank you.